Right, welcome everybody to the second of 5 sessions in our Knowledge Zone offering for 2024. We're going to wait just a moment for people to arrive, but I wanted to highlight the need for training and retraining for knowledge. So I shared transport with a colleague this morning. I'm coming into the office, and she was at a marketing conference yesterday, a course about AI. Now, it doesn't matter your opinion of AI, the point is it's changing fast. The presenter was so completely up to date on the topic and the current state that that he or she, I'm not sure, included an outline of a new software that was just launched on Monday this week. So my point is that knowledge changes, maybe not as fast in the building industry as AI is changing right now, but that's the point in us running the seminar. It's about understanding your impact on what you are designing or building and the need to apply new knowledge, especially as demands on energy consumption and things like earthquake performance require changes. So we can't keep on repeating what we've always done. That would be dumb. As people come in, I wanted to encourage those of you who are interested in coming to the in-person event on the 13th of June to maybe combine it with something else. So over that weekend, there's a Pink Floyd experience in Auckland, there's the Armageddon Expo, there's the Bonsai exhibition and convention, there's all sorts going on in Auckland that weekend. I wanted to point out, and what we've got on screen there is that in-person event is our live webinar, which is also live streamed. So live in person and live streamed. The registrations are separate on our website, so they're both 13th of June there, as you can see. So please check which one you are booked in for. When the live stream finishes, those with us in Auckland in person, we will make available a hands-on experience with installing product on our training walls. We'll have a decent feed, and then we have a professionally run quiz night as well. So let's get started on today's topic, which is a dig into B2 durability and a discussion on the how should we build. Today, presenting this session is Richard Hollard, who I'll introduce in a moment. The last session, we touched on B1 structure and looked at some minor structural element changes that can make a demonstrable difference to the thermal performance of a construction. B1 was the first in this series because that loosely matches the sequence of building, the structure and stability first, including today's topic, durability. And then, weather tightness elements are added. That's the part 3 in a couple of weeks on external moisture, E2, followed by H1, energy efficiency, and followed finally by what we've called the naughty child, E3, internal moisture. During this presentation, we welcome your questions, your comments and your objections, and where possible, we will answer those questions along the way or at the end. Please use the chat function on your screen. And the chat box, we will post links to you during the presentation of anything that we discuss or we want to share with you. If you have a question, please use the question tab. NZRAB CPD points, 10 points for this presentation that we load for you, and 1 LBP point that you can claim for yourself through the portal. During the presentation, we have a couple of poll questions that will be answered by 2 of our national team. We have Simon Cater, based in Auckland, who presented last week, and Ben Ingledew, who's based in Christchurch. We'll bring them in to briefly discuss poll questions, and they'll be available at the end for our Q&A. So, Richard Hollard, he is our Specifications Manager and Regional Sales Manager, covering Auckland and Northland. Sad story, Richard used to ride and race motorbikes, but these days he's confined to riding a hardtail mountain bike. His dreams and aspirations are not of seeing his children flourish, but of owning a bike with more suspension and more horsepower. He has 18 years in the building industry now. Richard's skills and experience started with a background in science, having studied in Palmerston North. And like several of our team, he's also spent time on tools as a builder's apprentice, and so he knows a thing or two. If you've read or seen anything of ours in the EBOS Architectural Library, the articles and blogs, or on ArchiPro, or soon on Build Review, or if you use MasterSpec or SmartSpec, Richard is likely responsible. And on that subtle but shameless advert, I'm going to hand over to you, Richard, to tie B2 durability into the blend of code clauses. Over to you.
Thanks, John, for that wonderful introduction. Yeah, so B2, let's get into it. Okay, so make sure my mouse is working. So starting off with a lovely image here of a house in Auckland. Beautiful view of the harbour, Rangitoto Island, wonderful views, you know, perfect location. It's actually situated on one of the most expensive streets in Auckland, so it's definitely, you could say, the worst house in the best street, but not in a good way. There's nothing wrong with the materials used in this build, in this house, and that's sort of a shocking thing to say when it doesn't look too nice. You know, the paint was good, just hasn't been really maintained. The fibre cement sheet was good. It's a material we still build commonly with today. And same as the timber frame. The timber frame we still build with timber framing. Aluminium and glass haven't really changed much. They're still aluminium and glass. And we're still building with lightweight timber framing and with plaster finishes. But something clearly went wrong with this build. And if you look closely, you see patches, mildew, mold, general degradation. You can even smell, you could probably almost smell that building from here. It's pretty tragic. So durability in the context of building materials refers to the ability of the materials to resist deterioration, weathering, corrosion, and other forms of degradation or decay from either internal or external sources. And we've got to consider both here. Durability is crucial in ensuring that buildings and structures remain safe, functional, and aesthetically pleasing throughout their expected lifespan. So in this image, the combination of the design, how the materials were used, combined with the obvious lack of maintenance, left little room for error. And when water makes its way past the silicon beads and the paint coating, there's little chance of the construction drying out and remaining durable. There's a lot of talk about sustainability in construction these days. It's a big focus, you know, green stuff, sustainable stuff. And there's a big focus on what we're building with, the use of things like solar panels and reducing waste. But really the most sustainable building is just the one that keeps standing without having to be rebuilt every 15 years or so, irrespective of what it's made of and what direction the view is. If we look at the high-level objectives of the building code clause that we're talking about today, clause B2, durability, it's perfect. You can't really do much better than that. You know, make sure that the building throughout its life continues to satisfy the other objectives of this code. Make sure it's doing that without having to be reconstructed or renovated. You know, we hear a lot about bagging the code, and probably some of you coming on today thinking that we're going to be pulling down the building code and bagging it. But if we look at the high-level objectives, we can't really fault it. It's really the acceptable solutions within the other clauses where it gets let down. You know, what's been allowed to happen in the past allows for failure to occur. The 5 clauses that we talk about in this series of webinars are all heavily interconnected, probably as you'd expect. But the compliance with or lack of compliance to one clause drastically affects one or the other clauses. B2 durability that we're focusing on today could be said to be set in the middle of the other 4 clauses as a characteristic of the products or systems used to satisfy the other clauses. A less durable cladding, E2, will affect B1 or the structure eventually. And the performance of H1, energy efficiency, as the insulation is impacted by external air and moisture ingress and internal moisture ingress as well. But it's more complex than that. We can add more connections between the clauses, such as too much timber for B1, affecting how much insulation we can add in to satisfy H1, which Simon was talking about in the earlier webinar. And the lack of internal moisture control affecting both the performance of H1 and eventually the structure or B1. So material selection is one of the key factors that we can focus on in terms of making a durable building. We need to consider factors such as the strength of the material, weather resistance, and the resistance to corrosion, degradation, or decay. And in New Zealand, we have the trifecta of big problems to work with in the form of high rainfall, strong UV, and regular earthquakes. Some building materials such as stone could be said to be more resistant to moisture and other stresses, while others like timber and steel are more sensitive and need to be treated appropriately. Material selection could be governed by a number of factors, including availability, ease of use, costs, aesthetics, available expertise to install, which is quite a big one we see, You could have a really good product, but if there's no one to install it, then it doesn't get used. And some countries predominantly build with solid masonry, and often we ask the question, why don't we do that in New Zealand? And it's due to probably the cost of labour in those countries, availability of materials. Here in New Zealand, we tend to build mostly with timber because it's fast growing, it's plentiful, and reasonably well priced, or it used to be. But if it's not protected adequately, it can impact on the performance and durability of our buildings, as we're too well aware. So why do we have an issue with timber durability? There's many examples of old timber buildings around the world. So the temple on the left-hand side of the screen there is the oldest timber building in the world, with parts of it now over 1,350 years old, which is pretty amazing. The reason why more of these old timber buildings haven't survived is often due to fires or buildings being replaced, but not from decay. If this one survived, why didn't the one next to it survive? Surely the timber we use for framing in New Zealand is much softer than other species and has no natural protective properties as some timbers do. But we know if we protect it properly during construction and for the life of the building, it can be made very durable. As mentioned in the earlier webinar in B1, is when we started adding insulation to the mix around the late 1970s that problems with our timber framing started occurring. By its very nature, insulation is designed to slow down the rate of energy transfer, so the rate of drying from air and moisture flow through the building slows down, which increases the potential for issues such as mold, decay, and rot to occur. But if we make provision for suitable wind, water, air, and moisture control layers in our designs, we can ensure the durability of the timber components, be it a lightweight timber frame, mass timber panel, cladding, or lining. So what we have here, an image of a chair in a house. The chair on the screen is one of John's favourites, made by Woodwrights of Tasman. They're at the top of the South Island there. So this upholstered side chair is valued at $1,362. Beautiful piece, designed by Jeremy Invison in 2023. I think John's got, is it 6 of these or 8 of these at your house, John?
Nice. None.
Yeah. So even though they are beautiful pieces, well built, solid chairs, they're not designed to be used outside. They're not made from treated timber, but they will last. They will last for years if the house is not mouldy. They won't go mouldy or suffer from decay unless the area that they're used in is cold or damp, or if it's a spa room or a pool room, or just an unheated, unventilated house. So the real question is, why do we need to treat timber frame? Isn't it an admission of failure, or are treatments only a temporary solution? At what point of the building, from the inside to the outside, do we need to start treating the timber? If we place the same chair within the external wall and pack insulation around it, what happens? As mentioned previously, the rate of energy transfer and drying slows down, so the risk of mold or decay of the timber increases as it's now situated around where the dew point occurs between the interior and the exterior of the building. Treatments will help preserve the timber for longer in this case, but won't stop mold or decay occurring on surrounding materials. If there is more wetting than drying potential, the durability of the timber will be affected. If we then shift the chair to the outside, we know from experience that it will start decaying quite quickly unless we adequately treat it for exposure to the elements, or if it was made from a hardwood or another species of timber with natural protection. The chair gets wetter outside, but is also able to dry out more quickly than when placed in the wall. So it can be quite durable, as we saw in those old timber buildings. Over to you, John, for the first of our poll questions.
Great, thanks for that, Richard. I think those are nice chairs, and I don't own any of them. They're a little bit spendy for me, but I think the question is exceptional, actually. Like, at what point do we start treating? So and why do we need to? So the first question that we have as a poll question for our attendees today is, what level of treatment should be selected in a timber wall? So this is more of the question of where are we at right now with design and what you are involved with. So whether you're a designer or a builder, what should be selected in a timber wall? Is it H 3.2? Fairly heavy green, is it H 3.1? LOSP, is it H 1.2? A nice pink timber, or is there no treatment required? So that is our poll question. If you'd like to drop your answers into that poll, we'll give just a pretty short space of time for this one. So what should be selected?
I get the feeling that you guys are trying to get some free furniture out of this. Is that what you're trying to do?
Advertising wood rights. Yeah, I tell you what.
Who, sorry?
They do have some beautiful furniture.
It's beautiful that we can get furniture made in this country. It's great.
Was that woodrights.co.nz? Yeah.
Yeah. All right. Hey guys. Well, so we've got Ben online now, and Simon in Auckland, so Ben in Christchurch. So you guys, do you want to start responding to that? So what level of treatment should be selected in a timber wall? Well,
predictably, we've got the H1.2 should be selected inside a wall. And that's and why is that? What is that? That's a function of the building code, or our acceptable solution. It's good to see that people are aware that it needs to be treated. However, Simon, I don't know what you feel. Is that the right way for us to be going? Is it, surely if a wall is going to be built, why does it need to be treated? It's going to be built correctly, and so it's dry. Why does it need to be treated at all?
Yeah, well, exactly, Ben. I mean, if you're going to create a construction where you've got a guarantee that you're going to be keeping that timber dry, then I'm sure you'd agree with me. You probably don't want something like arsenic hanging around near where your kids are playing.
Exactly. Yeah, I can see that somebody actually got.
You're trying to stir the pot there, Simon. Yeah. Hey, look, I'll point out too, and I think, Ben, you were about to. So there's a few people that have chosen H 3.2, and so I can understand why that might be the case for a bottom plate in a structure where that's going to be wet for quite a long time as part of the build process. I can start to understand that, but that again is what we're trying to look at is the long-term view on a building, and the question is, can we get to a stage where the treatment of the timber is not required?
I think, John, it's all about looking at trying to get a system where you've got more of a drying capacity and less of a wetting capacity in your wall.
The reason why we treat the timber, of course, is to mitigate the mold growth. That's a new term, that. The mold growth, because once the mold gets in, it starts to grow, and the chemicals in there reduce its growth and prevent its growth. But if it's not, then the other way to do that is to keep the wall dry. Mold won't grow if it's dry, and it won't grow if it's got the right temperatures. So it's about designing the system correctly and obviously using the correct products to do that.
Okay, so the final part of that question then is, will a treated timber in a wall actually make the building better if it's wet anyway?
Oh, no, the wall's still not going to work, is it? If it's wet.
So what I'm just trying to feed in there is this idea that if we've got a poor design or poor products that feed water into the wall, and that's this image that Richard had on screen right at the beginning as a poor construction. So actually, and that helps us too. So the question behind all of this is, at what point in a wall do we start treating from the inside of the wall to the outside? Yeah, we can appreciate that a pine cladding on the outside there, number 6, might be treated, but what else? What about the architrave, Ben?
Well, you start at 6. You've got a cladding type. Depending on the type of cladding, cedar doesn't need to be treated because of the resins within it. But then you've got 5 going through. Okay, a batten, treatment going to be useful. It's going to be exposed. But as you work your way through, I mean, we've got framing there at 4. Well, why should it be treated? Why should it be wet at all? Is it some part of the system must be failing? if that's going to have high relative humidities.
We can see it nicely protected by layers either side of it. So, you know, if they're done right, yeah, would it need to be treated?
Simon, what about number two? What about that? Sorry, Ben. Simon, let's just move on a tiny bit. But what about number two, that timber liner? Because that's typically a 3.1 H3.1 timber, a pine treated liner. Why does that need to be there?
Yeah, and John, why exactly is that? It's all about that we're expecting to find condensation, perhaps on our glass, but certainly if you're looking at aluminium window frames, we're definitely getting a condensation forming on there if we haven't correctly created thermal breaks in that system.
So guys, let's finish it there. Thanks for that. I think just the summary of that is let's start looking at our design and the performance of the elements all together in the building, which help to prevent moisture accumulation. Brilliant. Thank you. Thanks, team. Richard, back over to you.
Cool. So what does happen to timber when it gets wet? I mean, not only there's mold growth and general starting decay, it moves as well. It changes shape. So the wetting and drying cycles of timber change the size of the timber cells, which when it dries, it makes it warp or distort, changes direction. So the quicker grown, less dense timber that we use in our buildings is more affected by this, by the temperature and humidity changes than maybe the harder woods would be. But if we can keep the timber at a stable moisture content and temperature, it will stay straight or happily in one position and put less stress on surrounding materials. Bingo, no nail popping. Well, we've got some nice nail and screw popping here in the images. So the effects of that of the timber movement include cracking of joints, nail screw popping within external and internal surfaces. It's not only unsightly, but becomes it's a costly maintenance issue to fix this up, get the jib stopper in and fix it up, but also potentially impacts on the durability of the structure by allowing internal and external moisture ingress into the building envelope. So we've got some screws popping through the ceiling lining there. In the middle there, we've got a screw popping out of a cladding on the outside, and also some cracking on a external surface within a cladding, and also some screws popping through a ceiling to wall junction as well down the bottom right hand side as well. So all this could be avoided, I guess, if the timber is not changing and moving temperature and moisture wise. So another thing to factor into, and this is a big one to factor in for aiming for durability, is the design. Materials construction methods should be suitable for the specific climate to minimize deterioration. Flat roofs and no eaves works well in hotter, drier climates such as Greece, as in the image here, but they also build mostly with solid, less moisture sensitive materials. And let's face it, I've been doing this for a few years now, so they've most likely learned what works and what doesn't. As we know too well, in the 80s and 90s, we tried to replicate the no eaves flat roof style of the Mediterranean, but with the lethal combination of moisture sensitive lightweight timber framing, complex junctions, and unprotected high risk direct fix claddings in a much wetter, colder climate. Throw in a high dependence on sealants and paint as the last lines of defense. The only possible outcome was disaster. As building scientist Joe Steebrook says, we did some dumb stuff in the past, but we weren't the first to do dumb stuff. The Canadians and the Americans after them both build with similar materials to us. They did dumb stuff as well, but we didn't learn in New Zealand from their mistakes like we should have. Are we still doing dumb stuff now that will fail in the future? Let's go to one solution to avoid popping plasterboard fixings. Keep the frame dry. Structures which are designed with clearly defined building control layers are better equipped to withstand both internal and external forces and will be more resilient. The detail on this slide is a cross-section of a best practice lightweight timber frame wall with insulation between the stud frame. So on the left-hand side, we have the wide grey crosshatch line, which is the water shedding surface, otherwise known as the cladding, and the 4 Ds of moisture control. This is our deflection layer. The blue dashed line shows the weather resistive barrier or building wrap underlay membrane, which handles both external moisture and is also wind tight while allowing drying in the form of vapor diffusion. We can ignore the rigid sheathing board in this example for now. That handles more wind pressure. Next comes our fluffy insulation thermal control layer, then the red dotted line, which is an internal air and vapor control layer. The next two bits don't really do anything to protect the timber frame from moisture. A bit more insulation in the surface cavity and the plasterboard lining. This is important. The plasterboard lining or layer on the right-hand side of the image then doesn't have to perform any important role. It's not being relied on to control air or internal moisture, as it often has penetrations in it, and the likes of power points and light switches. So it's mainly for aesthetics and protection of the layers beneath. To be fully effective, all these control layers, the blue and the red and the insulation layer and everything else, which is labelled as a control layer, needs to be continuous right around the building envelope. And it's not just on the walls. But these layers can be made up from different materials. So on the floor, often on a concrete floor, that is our air tightness layer across the floor. Designs which recognise and allow for both control of internal and external heat, air and moisture sources allow for durable building because they can be planned with more drying potential than wetting possibility. So we've got to keep the dry and kiln dried before, during and after construction. Similar sort of thing here, but with a mass timber panel. Despite it being a different construction system to lightweight timber framing, we still need to incorporate the same building control layers, that is water, air, vapor and thermal, to guarantee long-term durability of the structural element. Here we shift the insulation to the exterior of the mass timber panel, as we don't have those handy little pockets to put fluffy stuff in. Installing all or most of the insulation to the outside of the CLT ensures the temperature of the panel remains relatively stable and above dew point year round. The dew point will then occur to the outside away from the moisture sensitive timber, which is ideal. In this case, the weather resistive barrier to the outside of the panel protects the timber from weather during construction and acts as the air tightness layer because it's to the inside of the insulation. The one major change is the type of insulation which is used. Often it's a rock mineral wool or timber fibre insulation in this case, because they're denser and they're not affected by wind wash like the lighter insulations we use within our walls. Rock mineral wool is also extremely hydrophobic, so it won't hold on to moisture, which is not a bad attribute to have for an external product. So like with the timber framed example, with good design which recognises and allows for control of both internal and external moisture sources, we can build structures which remain dry and durable. Same sort of thing here with concrete. In this case, we're trying to protect the steel elements within the concrete from corrosion, not the timber from going mouldy. Anytime we stick all or most of the insulation to the outside of a solid material such as concrete, it becomes easier to maintain a constant temperature within the building as the mass is held at a more constant temperature, not radiating heat into the building or sucking heat out of it when it's cold. And this detail is basically the same thing that you do for a steel frame. Put all the insulation on the outside and avoid the thermal bridging. So the 4 Ds, while the likes of paint coating and timber treatments give us more durable external finishes, without good design and the right materials to allow for deflection, drainage and drying of moisture sources, the preceding layers within the building envelope cannot be expected to achieve the required or expected durability. We often look at the 4 Ds as being equal. You've got deflection, drying, durability and drainage. But really the equation should be deflection plus drainage plus drying equals durability. Even if the most durable materials are used, if the other 3 Ds aren't adequate, we end up with total system failure. And over to you now, John, for the next poll.
Awesome, thank you, Richard. Hey, just wanted to cover a couple of quick things. There's a couple of great questions that are popping up already. One of them is real simple. Is there access, if we didn't see the last seminar, can we get access to that? The answer is yes, and we've put that in the chat. We've put the link to the previous webinar, the recording of that. The second one is a great one, and it is moderately simple, so I'll answer it really quickly. What is the difference between 3.1 and 3.2, and then differences H5, 3.2, 3.1? So very quickly, H5 we didn't talk about because that is a heavy duty treatment, which would be for a timber which is going to be placed subgrade. So below ground. So H3.2 we have talked about. H3.2 is quite a heavy green looking timber when it's dry, and even darker green when it's wet, and that is a CCA, or a copper chrome arsenic treatment in that timber. And 3.1 is a lighter weight treatment, but it's a different treatment, and it uses it's commonly called H3.1 LOSP, so light organic surface preservative, or a solvent preservative rather. So it's carried into the timber on a solvent, which means that you can also wash it out of that timber as well with water over time. So hopefully that's of use. So there are differences between 3.2 and 3.1, and hopefully that's enough on that for now. So let's go to the poll question. So this is getting into the nitty-gritty of it really. This is for both designers and for builders. When will you choose as a designer, or when will you push your designer, if you're a builder or some other place in the construction industry, when will you choose non-treated timber frame? The answers that we've put there: no way, not ever, forget it, you're stupid, thank you. The second answer is only with external insulation. So if you've got a system like Richard just shown on screen with CLT or concrete, where the insulation has to go outside anyway, sensibly. Third answer there, if it has a code mark or some sort of certification, or if you're going to promise that it's going to work, then I might choose it. And fourth answer is I already do. So let's have a look as those are populated. And I want to say, just as we do that, that I just realized during Richard's last piece there that we're not anti-treated timber. We are pushing the other way to say, can we do these things without treatment? Can we build, especially timber frame, without treatment? All right, how are we going on the answers to those? Oh, love it. Okay. Ben, Simon.
Interesting split.
Yeah.
I did notice
Yes,
as I was watching the votes come in, I noticed there was one person clicked I already do. They were the first person to vote, because you can sort of watch them come in. So somebody yep, I already do choose non-treated timber. Yeah, but what we've got, no way, not ever. That's an interesting outcome there. And then there's a bit of a split between only with external insulation, and the other one was result there was about it being code marked, 26% if it had been code marked. How do you read that, Simon?
Yeah, Ben, I think once again, it's all about protecting it properly. So if we're doing an external insulation system and we've got our structure well protected, or if we've got a timber frame where we've protected it both from the outside with a weather resistant barrier that's taped off correctly and will perform properly, as well as something to control airflow and vapor from the inside of the building, which will maximize the drying capacity and minimize the wetting capacity of that system.
And but what we're advocating here is not, like John just said, it's not about removing. We're not here to remove treatments. What we're here to do is design so the timber stays dry. And it's that dry by design that we've talked about before, or the perfect wall that has been mentioned. It's about that wall not requiring treatment. Yes, if it's in the code, use it. You know, if that's what you want to do, it's a belt and braces approach. But surely we should be putting more energy into making sure that wall just never gets wet in the first place. Interesting point as well, John, about you said about the treatment washing off. It's actually, you know, it's put in under pressure, isn't it? the treatment. And if that timber frame is exposed and left out in the weather for 2 or 3 months, rain and sun, the treatments can be just wash out, and you'll get mold appearing in a wall, even if it has been treated, if the conditions are encouraging mold. So yeah, we're obviously, the way people are voting, it means we've got a split of thinking. That's great. That means we've got at least people are thinking. That's really good.
So just on my last bit on that then, the answer there, if it had code mark, now that was a general sort of thing around, you know, can you convince me? I think this is the point, or can you promise me that it works? So Simon, what's, from a pro-Clima perspective, what's our promise, I guess, in the back of that? And this might come up a little bit later in Richard's presentation too. So do you want to cover that?
Well, John, it's all about you know, modeling that the system is going to work correctly, isn't it? Using something like WFI modeling to ensure that you actually understand how that buildup is going to perform, and then obviously constructing it to the correct in the correct manner, so that you can have a system that is going to work properly. I mean, we already know many countries in Europe, timber treatments are banned from use, so it can be done correctly.
Great, thank you guys. All right, Richard, let's hand back over to you.
Perfect segue into the next slide there, because funnily enough, we are talking about the wonderful WFI. So, I mean, quality control is a big one to ensure durability. And one of the things we can do to ensure quality control is to hygrothermally model our construction during the design stage to ensure that it's not going to get wet, or make sure that we can change it so that it doesn't. So WFI is a hydrothermal modeling tool, modeling moisture and heat flow through construction, through wall and roof systems. The word WFI is an acronym for heat and moisture flow in German. I'm not going to attempt to say it because I'll probably embarrass myself. My German is still at the kindergarten level, you could say. So moisture management is the key to building performance, durability, and health. We've got to encourage, as we've already talked about earlier, more drying than wetting. So what WFI does, it's a software tool. It's developed by the Fraunhofer Institute, which is like a bigger version of Brands in Germany, building research facility. They do research on lots of other things as well. And it's been developed to be able to be used anywhere in the world. So you plug in your climate, if in this case here on the little simulation there on screen, it's a building in Auckland. So it's got all the NIWA weather data in there for Auckland, the temperatures, the humidity, the rainfall, the wind, the UV, everything like that. So that's all in there. So that's real specific to that location where you're building that building. Then you plug in your wall or roof materials that you're using. In this case here, we've got a brick cladding that's 80 millimeters thick. We've got a 40 millimeter air cavity. We've got a 4.5 millimeter. It's confusing because Europeans put everything in centimeters. A 4.5 millimeter rigid air barrier, and then we've got our insulation layer, and then a jib lining on the inside of there, plasterboard lining. Each of those materials has different properties of heat, moisture absorption, vapor permeability, moisture storage, capillary reaction. So they all, and when you put them all together and you add in the internal conditions as well, what moisture sources there are inside, what's the occupancy, is it an airtight construction, what's going on inside, and then we can quite accurately predict basically how heat and moisture is going to flow through from inside to outside and from outside to inside throughout throughout years. So we can see here the little clock whizzing around like crazy. That's modeling this build up over 5 or so years, I think it is. The red line at the top is the temperature gradient, so that's fairly stable inside, moving a lot more around on the outside as we'd expect. The green shadow and line is the relative humidity within that construction, and we know that if relative humidity stays up above 80% or more for, doesn't have to be that long at all, 1 or 2 days in some cases, if the temperature is right, we get mold growth. So we're wanting to ensure that the relative humidity throughout a construction with the combination of materials and the right design, how those materials are used, stays below 80%, or if it does go above 80%, it drops down pretty quick, is able to dry out basically. And then the blue line and the blue shadow area is the water content. So brick claddings on the outside, they can absorb a lot of moisture, but the reason they work well is because they've always got a ventilated or a drained cavity behind, and it can drain out. So woofie really, instead of our little brains trying to work out how all these things are going to work together, the climate, the materials, what's going on inside, combination of all those things, woofie takes all that out of our basket and calculates all that based on research, and can quite accurately predict whether there's going to be mold growth in the moisture sensitive timber-based type products, or corrosion of steel components, whether it be a reinforcing or a steel frame or something like that. And so it's taking away the guess factor. It's giving us a real educated guess specific to that location. So things like orientation of the building are considered in woofie, whether it's west facing or east facing or whatever. The angle of the roof, that has an effect as well. The color of the cladding has an effect. If we've got a white colored roof and a south facing orientation anywhere in New Zealand, it's going to remain cold right throughout the year, and so the drying effect is going to be a lot less. If we've got a dark facing cladding facing north, facing north, well, that's going to be hot most of the time. It's going to be harder for the probably assembly to remain cool, but it's going to actually dry really well as well through the year by that heat and air movement in that in a cavity. So woofie, a tool for quality control at the design stage, can be used for sensitivity analysis to sort of take in and out layers, different materials, different types of insulation, to work out what's going to work and what's not going to work from a moisture point of view. You know, what's safe, what's going to keep dry, what's going to be a problem even 5-10 years down the track, which is pretty hard for us to accurately predict just by ourselves. So great tool to use. We promote the use of it. There's the woofie.co.nz website there. We also do the training in this program. Our technical manager in Australia, Jesse Clark, he's the woofie guru. He does the training. So if you don't want to spend on the training and the software itself, you can go to that website. You can go to the woofie professionals, and you can get your design modeled by a woofie professional that uses the program and has had training in it. So great tool to use. Go check it out. At the construction stage, a quality control tool for the builder is the blower door. So while at the design stage we're using woofie, and it's sort of conceptual, where we're proposing what's going to happen and seeing what's going to happen, quality control at the design stage is all about the installation, checking whether the installation is as per the design and as per what the manufacturer recommends. So what a blower door is a tool that a big fan that you put into a canvas skin, goes into a frame, goes into a door or window opening. You close all the other windows and doors. You crank the fan on using the computer. It can be controlled off a smartphone now, which is pretty cool. And then if you've got it set on depressurization, you're sucking air out of the building. Air's coming back in all the gaps and cracks around the building envelope. So what you're finding is all the unintended air infiltration pathways, which used to be called passive ventilation pathways. It's not ventilation, it's infiltration. You're trying to measure or see where air is coming in and out of where it shouldn't, basically. We want air coming in and out of windows and ventilation systems, but not necessarily through random areas of the building envelope, because that's where interstitial condensation can form when warm air touches a cold surface. So good quality control tool to use for the builder during the build stage. It's always used in a passive house, because they've got a, when you're doing a passive house build, you've got to do a blower door test to find out whether it's meeting the requirement or not from an energy efficiency point of view. But we'd recommend a blower door test or some sort of type of verification used for any build, because what you're doing is you're just ensuring the quality of your build. It's going to be free from interstitial condensation forming. It's going to be more energy efficient. It's going to be a better build, a better result for your client if you put in your specification to do a blower door test. Set a reasonable target for that type of construction that you're doing, and everyone's going to win at the end of the day. Maintenance is a big factor also in durability. You know, and we quite readily wash our cars. It's a bit of a fun thing to do, get the kids involved, and we do it regularly, and we're quite proud of our cars sitting there nice and clean. And it's a bit of a statement, but we understand that if you don't wash the car often, you know, the paint suffers, and we don't get the chance to look around the car and check whether it needs fixing up or not. But what if we took the same approach to house washing? You know, it's recommended by the paint manufacturers and cladding manufacturers to regularly wash houses, you know, every year, and if it's a paint coating, recoat it every 5 to 10 years. The buildup of salt, bird droppings, you know, UV degradation, other airborne contaminants can affect the surface coatings or paints on the outside of our houses. And if they aren't washed regularly, then they can start to degrade, which affects the durability of the layers beneath. So it's a question that I've often thought about is we wash our cars on a regular basis, and our houses are more expensive than our cars unless we own a Ferrari and live in a tent, but we don't regularly wash our houses that often, but the durability will suffer if we don't. So that brings us back to design, really. The building we see in the image here is an eye-catching design, but we need to consider the maintenance. How easy will it be to clean this facade or maintain it? We need to consider the complexity of our designs when aiming for durability. The more complex the design, the less likely it is to be kept clean, or a higher chance there is of dirt or debris building up and affecting the drying ability of the construction. Structural integrity is one of the key factors, as discussed by Simon during the B1 structure webinar. The key to total building performance is not letting the requirement for one building code clause affect the performance of another building code clause. For example, as Simon's discussed earlier, we see additional framing being added to meet B1 requirements to the detriment of H1 energy efficiency, which increases the risk of moisture-related issues such as mold or decay occurring, meaning we no longer have a durable structure. And we often joke when we see the framing on the left-hand side there that the CLT machine must have broken, because it's almost a solid timber panel, but not quite. Almost better to just put external insulation in that type of build. So to summarize, we need to consider the relationships between the code clauses really well. We need to design with and build with drying in mind. We need to use the tools and quality control tools to verify our design and build, and we need to keep up the maintenance. Over to you, John, now for the questions.
Brilliant. Thank you, Richard. Hey, I've got one for you just as a quick kick-off, nice and easy. There's a reaction to the poll discussion. They've said no fall in the sill either, so they're referring to the image that you used, and we discussed this before the presentation. Just want to quickly cover, what was that? Was that an image in plan or of a jam, or was that sill? What was that one?
That was yeah, it's actually a jam. By just the way that fitted on the page, I just switched it around that way. So it's actually a jam. Not a sill. Well picked up there. Yeah, falls for sills are pretty important. Yeah, well picked.
Good. Okay. And actually, I'll follow on with another one for you, just to put you on the spot. The question following that is, well, not related to that one, but will plasterboard cracks and popping fixings, will that occur when the building is moving generally? So let me load a bit into that. Will it prevent popping if there's significant or any seismic movement, say?
Yeah, I guess seismic movement is another thing to consider. That's harder to isolate yourself from. But by keeping the timber dry and at a constant temperature, you know, that can massively reduce the movement within the building. But yeah, and if it's insulated well as well, that will that's, you know, the temperature is kept more constant. Yeah, buildings sort of creaking and groaning sometimes as you know, the day heats up or cools down. The better the insulation, the better we isolate or protect ourselves from thermal movement. But yeah, seismic movement, that is a good point, especially in New Zealand, certain parts of New Zealand. It's going to be harder to isolate ourselves from, unless I guess we put our houses on water, like on in some European canals, or you know, a big sort of rubber pad or something under the house.
Cool. All right, I'm not sure whether there's going to be more movement on a canal. But anyway, hey, that's great. So Simon, I'm going to hand a question to you. So the question is, how do you achieve air tightness in the example shown with CLT panels? And the second part of that question is the airtight, or will the airtight membrane be punched by the fixings for the insulation and cladding?
Yeah, great question, John. So with a CLT panel, we can't generally assume air tightness. So often the air tightness with CLT would be created by using such as a peel and stick building wrap on the outside of the CLT panel. And we can ensure that we seal the fastening penetrations by using something like a butyl-based tape that can be installed behind the rail or the brick tie or whatever we're fixing to the outside of that system.
Oh, thank you. And then the follow-up question around that then is the air tightness testing. So the question stated is air tightness testing to be done without insulation installed. So the question is, how do you do air tightness testing of that, I guess for us, that blue layer outside? What's the mechanism for fixing that if there's a mistake?
So John, a key thing, obviously, we'd use the blower door for testing for air tightness. Just to mention, we do have a list of blower door testers available on our website for people if they're looking for blower door testing. When you're doing the blower door testing, you would need to have access to that layer. So ideally, this would be done prior to the installation of the insulation so that you can get access to that layer and rectify if there are any leaks in that system.
Cool, thank you. Hey, we've got a couple of good reactions to some of the poll discussions. So there's a comment from, I'm assuming somebody in the South Island, but New Zealand, Oregon with 600 eave overhang is the acceptable solution, and it's common in the Lower South Island. Ben, do you want to hit that one, given that you are almost in the Lower South Island, not quite?
Well, I'm in Canterbury. I have seen it. I've got friends who have used Oregon framing here in Canterbury as well. And that's the eaves. I'm a big fan of eaves. I meet a lot of architects who don't think they look slick enough, but I wonder what looks slicker, mouldy walls or eaves. So yes, you certainly can do that, and that's because of the natural resins within the Oregon that protects it from the mold, combined with a good weather protection from the eaves. And that's about systems again. So it's about materials and systems in combination.
Good. All right. Yeah. So design. Okay. My borer seem happy to eat untreated timber no matter how dry it is. Again, let me possibly answer that. But again, it's not about not treating, but it's about better design to prevent water, bulk water washing through or moisture accumulating in our structure, in the frame, and doing damage. And that again, not that borer eats steel, but it's the same thing, right? Steel corrodes, rots, whatever you want to call it, rusts. That doesn't like water. Neither does timber. We want to try and prevent that from getting wet. Borer, different thing. So great. Okay, our next reaction to the poll, Ben, I'm going to throw this one to you, I think. If we build in a controlled environment, we can use untreated timber, but we are typically building in the elements. Ben, what's your commentary around that?
Yeah, interesting, because it does take time to build a house, and your timbers are exposed to the elements. And what's really important, and they will get wet and they will get dry during that build phase. But what's important is for the long term, what's going to happen. So in the build phase, the timbers will get wet and dry. But as soon as they're wrapped up, what then needs to happen is that they are drying out, and they're drying out to the point where mold won't grow, and that's less than 70% relative humidity. Now that of air humidity. So of course, you need to do that in order to get your timbers dry in order to put your cladding on. You're not allowed to put your internal linings, sorry, I should say, on wet timber. It's got to be less than 12%, and that's with the moisture meter. So the whole idea is, yes, you can build your frame in the rain, that's fine. It isn't going to get it. The mold might take, if you had untreated timber, the mold might take hold, but that mold would very quickly die and perish once it gets dry, with the design, through the design and the material selection.
Cool. All right, hey, we're going to change topic a little bit here. We're going to go back to the WWOOFy software. Richard, I think I'll throw this one to you. So does the WWOOFy system provide the data by city location or exact address location? So let's assume that question sensibly is the NIWA data, the external environment. So do you want to answer that one for us, please?
Yeah, it's as far as I believe, it is as accurate as it's broken up as much as NIWA gives you options in your weather map. If you look at the NIWA app, you can and yeah, I think, I'm not quite sure, within Auckland there's probably 2 or 3 different locations, but I mean, it's a lot more accurate than saying, okay, I'm going to assume that the climate from another totally different climate from another country somewhere. Or New Zealand is quite diverse. There's a number of different climates within the country, but within Auckland itself, it would come down to the NIWA weather stations. However many of those there are in Auckland, I don't know, but it's as accurate as NIWA is accurate, basically.
Thank you. All right, question, not sure who to land this on, but would you still recommend a blower door test on a house being built without an internal vapor barrier? Who wants to pick up that?
Yeah, I mean, it's always a good idea. Yeah, you're checking you're checking the quality of the build, basically, and whether you've got a internal vapor barrier or whatever type of your construction is. What you're doing is, one, checking how energy efficient the house will be, how easy it will be to heat and cool, whether there's big gaps and cracks everywhere where the heat's just going to leak out all the time, and also checking the safety of the construction. So we recognise that without a dedicated air and vapor control layer, if you put a hole in the internal lining, it is harder to seal that. It could possibly be sealed locally around light switches and power points. Some flush boxes are more airtight now, but it is a good way of ensuring that during the design, during the build, while you're still able to, you're able to make that build as good as possible. Yeah, so there's a saying, sort of build tight, ventilate right, and that's true really for any type of build, whether it's a standard building code build or a certified passive house. Put a ventilation system in so you can guarantee that you've got air supply, fresh air change, no matter if windows are open or not. And use a blower door test during construction to make sure that the house is able to contain the energy. Ben?
Yeah, can I just add to that? I had a customer call me up and said, do you do blower door tests? And I said, yes, we do. I said, good. I've just had a house built. It's down in Twizel. It's very cold. I said, oh dear, that's not good. What are you? She explained they had 2 massive heat pumps, so that was, and it was ducted, so that it wasn't a lack of heating. She said it's drafty. I said, okay, right. So I said, well, I can come down. Let's say I came down and did a blower door test on your home. What are you going to do next? She said, well, I'll complain to the builder. He said, well, and what's the builder going to do? She was assuming there was some kind of building code or regulation around draftiness of a house, and there isn't. You can build a drafty house. There is no regulation or legislation about how drafty a house is. But there are air tightness limitations on windows, etc. But as a whole system, there's no limitations. So yeah, it's really important to know where your house is leaking and how it's leaking and how many air changes. But under current legislation, you can't use it as leverage. But that's going to change. We're looking at that. Everyone's looking at that. Brands are looking at the local district councils. Everyone's looking at the air change rate and working on setting a target for that. I know USA has 5, Australia has 10, which is pretty drafty. Denmark has 0.5. We're going to go somewhere We'll see what happens.
Yeah. So Ben, they have a target and we have no target, and so you know, a high target is better than no target.
Yeah, absolutely, yeah. Even if it is 10, but we've got to beat them though, haven't we? Isn't that the rule? Beat the Australians.
I was going to say, for those of you who are designers and use master spec, there is within our work section there on internal air tightness 4161 PI. There is a table, handy little table that you can refer to, maybe even if you're not using our internal air tightness products or not, to refer to give you some guidance on what target the air tightness target should be for the builder, basically to meet based on what sort of type of build you're building. We know there's targets for passive house, targets for Homestar houses as well, for other houses if you're just trying to do the best you can. So you can refer to that document. Maybe we can put that in the chat or you know, make that available somewhere as well.
Great. Hey, well, on that note, we're going to call it quits. It's 1 p.m. So just a quick wrap up, well, not wrap up, but just a follow on in 2 weeks' time. We will examine E2 external moisture, and we'll be asking the question, how hard can it be to keep water out? Because as we now know, a failure to meet E2 means a likely failure of B2 and therefore ultimately B1, and we just don't need to fail. So I'd like to thank you very much for attending, and also our panel, Ben and Simon, and our presenter, Richard Hollard. Please feel free to get hold of our team for in-house presentations, on-site assistance. We cover the whole country. We're still waiting for that call for Great Barrier Island. And on that note, thanks so much for attending, and we'll see you next time.